Today, we're going to prove that the square root of 2 is irrational. But wait, we're not using the traditional proof by contradiction. No assumptions, no old school methods. Instead, we will approach it differently, breaking it down step by step in a fresh and logical way. If you've ever wondered why the square root of 2 cannot be a rational number, stay with me till the end because we're about to uncover the truth using a new perspective. Chapter 1. What we need to prove. Let's start with the basics. A number can either be rational or irrational. A rational number is one that can be written as p divided by q, where p and q are integers with no common factors, and q is not zero. An irrational number cannot be written in this form. Our task? Prove that the square root of 2 does not fit the definition of a rational number, using logic, not contradiction. Chapter 2. Is the square root of 2 an integer? Step 1. Can the square root of 2 be an integer? Let's check. If p is an integer, then squaring it should give us 2. Now let's list some perfect squares. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Clearly, no integer squared equals 2. So the square root of 2 is not an integer. Chapter 3. Proof 1. Logical approach. Before we get to the mind-blowing second proof, let's start with a logical step-by-step approach to test whether is rational. Some may call it traditional, but we are going deeper into why this approach truly works. Since the square root of 2 isn't an integer, the next question is, can it be written as a fraction of two integers? Let's assume it can be written in the form p divided by q, where p and q are integers, and q is not 0. Squaring both sides, we get p squared equals 2 times q squared. This means that p squared must be exactly twice some perfect square. But does such an integer solution exist? Chapter 4, Testing Integer Solutions. Let's test small integer values for p and q. If p equals 1, then 1 squared is just 1, which does not satisfy our equation. If p equals 2, then 2 squared is 4, which means 2 times q squared must be 4. That simplifies to q squared equals 2, but 2 is not a perfect square. No matter what values we test, we find that there is no integer solution where p squared is exactly twice another perfect square. This leads to a key mathematical result. If a squared equals p raised to some odd power times another perfect square, then no integer solutions exist when p is prime. Since 2 is a prime number and this condition applies, there are no valid integers for p and q that satisfy this equation. This contradicts the very definition of a rational number. Thus, the square root of 2 is irrational. Proof 2, the geometric approach. This proof takes a completely different path, one that blends algebra with geometry to uncover something unexpected about the square root of 2. We start with the same assumption. Suppose the square root of 2 is a rational number. That means we can write it as a fraction. P divided by q equals the square root of 2, where p and q are integers and q is not 0. Now let's square both sides. P squared equals 2 times q squared. But now, here's where things get interesting. Let's introduce an equation that might seem unexpected at first. P squared minus q squared equals q squared. If we rewrite this equation, we get p squared plus I squared times q squared equals q squared. Now dividing everything by q squared, we get p squared over q squared plus I squared equals 1. Since we define p squared over q squared as x squared, we can rewrite it as x squared plus I squared equals 1. Now let's step away from the algebra for a moment and look at what this equation means geometrically. The geometric interpretation. In a right triangle, we have the famous Pythagorean theorem, which says a squared plus b squared equals c squared. Now comparing that with our equation, x squared plus I squared equals 1 squared, this suggests we have a right triangle where one leg is x, the other leg is I, an imaginary number, the hypotenuse is 1, and here's the problem. In real-world geometry, all three sides of a triangle must be real numbers. You can't have an imaginary length in a physical triangle. What does this mean? This contradiction tells us that assuming the square root of 2 is a rational number leads to an impossible geometric situation. Since real numbers cannot form an impossible triangle, our assumption must be false, and that means the square root of 2 cannot be rational. Chapter 5, is the square root of 2 algebraic or transcendental? Now that we've proven the square root of 2 is irrational, let's take this one step further. There are two types of irrational numbers. 1. Algebraic numbers. These satisfy a polynomial equation with integer coefficients. 2. Transcendental numbers. These cannot be the solution of any such equation. So, where does the square root of 2 fall? We already know that the equation x squared minus 2 equals 0 is a polynomial with integer coefficients. Since the square root of 2 is a solution to this equation, it is algebraic. On the other hand, numbers like pi and e are transcendental because they do not satisfy any polynomial equation with integer coefficients. So, our final classification, the square root of 2 is not just irrational, it is an algebraic irrational number. This proof used pure logic, not the traditional contradiction method. If this method made sense to you, let me know in the comments. If you love logical math proofs and unique ways to approach problems, make sure to subscribe and hit the bell icon so you never miss an update. Also, drop a comment below. Did this method make sense to you?